For as long as we've had eyes to see the stars, we've asked the question, are we alone? Is there another Earth out there, orbiting another sun? This isn't just science fiction anymore. It's the driving force behind some of the most advanced astronomy today. And at the heart of this quest is the James Webb Space Telescope, or JWST. It's a time machine and a cosmic magnifying glass rolled into one, and it's showing us, for the first time, how rocky terrestrial planets like our own are actually built. Today, we're going to look at how Webb is pulling back the curtain on the creation of new worlds. Planets don't just appear out of nowhere, they are born from the leftovers of star formation. When a new star ignites, it's surrounded by a huge spinning frisbee of gas and dust. We call this a protoplanetary disk. Think of it as a cosmic construction site, a planetary nursery, where worlds are assembled piece by piece over millions of years. For decades, the most interesting part of this nursery, the inner region where planets like Earth, Mars, and Venus would form, has been a complete mystery. It's been hidden from us, shrouded by the very dust and gas that are the building materials. But this is where the James Webb Space Telescope changes everything. Webb is designed to see the universe in infrared light. This is a type of light that our eyes can't see, but we can feel it as heat. Crucially, infrared light can pass right through the thick dust clouds that block visible light. It's like having a pair of cosmic X-ray specs that can peer into the heart of these planet-forming disks. Webb has two key instruments for this job. The first is the near-infrared camera, or NIR-CAM. This is Webb's primary camera, and it's incredibly sensitive. It can detect the faint warmth given off by baby planets as they form, and it can see the fine details and structures they carve out in the disk around them. The second instrument is the mid-infrared instrument, or MIRI. If NIR-CAM is the camera, MIRI is the chemist. It's a spectrometer, which means it can break down the light from the disk to figure out exactly what it's made of. It analyzes the chemical composition of the gas and dust, giving us a complete list of the ingredients available for building a new planet. By combining NIR-CAM's sharp images with MIRI's chemical analysis, astronomers are getting the most complete picture ever of what's happening inside these cosmic nurseries. One of the most visually stunning things Webb can do is show us the architecture of these distant solar systems as they take shape. When a planet forms, its gravity acts like a cosmic snowplow, clearing a path through the disk. This creates telltale signs, huge gaps, concentric rings, and even beautiful spiral arms. Seeing these structures is powerful, indirect evidence that an unseen planet is there. But Webb can do even better. It can take direct pictures of these forming planets. This is incredibly difficult. It's like trying to spot a firefly next to a giant searchlight, because the star is billions of times brighter than the planet orbiting it. To do this, Webb uses a device called a coronagraph. It's essentially a tiny, precision-engineered mask that blocks the overwhelming light from the star, allowing the faint glow of the planet to become visible. In a landmark observation, Webb used MIRI's coronagraph to capture a direct image of a previously unknown exoplanet called TWA-7b. The image showed a tiny heat source inside one of the rings of a debris disk. After running complex computer simulations to confirm, scientists verified that it was indeed a planet. What makes this so significant is the planet's size. TWA-7b has a mass comparable to Saturn, making it about 10 times less massive than any exoplanet we had directly imaged before. This is a huge leap forward. It proves that Webb has the sensitivity to find smaller and lighter planets, pushing us closer and closer to the ultimate goal of directly seeing a world the size of our own Earth. Of course, knowing where a planet is forming is only half the story. To understand if a planet could be habitable, we need to know what it's made of. A planet's final composition is dictated entirely by the chemical recipe of the disk it grows from. Webb's spectroscopic instruments are giving us an unprecedented inventory of the raw ingredients available for planet building. And the number one ingredient we look for is water. Water is essential for life as we know it, so finding it in the right place at the right time is a huge discovery. Webb has delivered spectacularly on this front. It has detected water vapor in the inner, rocky, planet-forming zones of several protoplanetary disks. In one famous study, Webb looked at the disk around a star named PDS-70. This system was already known to host two large, Jupiter-like protoplanets in its outer regions. But Webb peered into the inner disk, at a distance of less than 100 million miles from the star, right where terrestrial planets would form, and it found water vapor. This was the first time water had ever been detected in the terrestrial zone of a disk that we already knew was actively building planets. This discovery also helps confirm a leading theory of planet formation called pebble drift. The theory goes like this. In the cold outer regions of the disk, way beyond where it's warm, water exists as ice, coating tiny dust grains and pebbles. Over millions of years, these icy pebbles slowly drift inward toward the star. When they cross a specific boundary called the snow line, the point where it gets warm enough for ice to sublimate directly into vapor, they release huge amounts of cold water vapor. Webb's instruments were able to detect this signature of excess, cool water vapor, right where the theory predicted it would be. This is powerful evidence that water is being physically transported from the outer solar system to the inner solar system, delivering this key ingredient for life right where it's needed to build a future Earth. But life needs more than just water. It needs complex organic molecules, the carbon-based building blocks of proteins and DNA. And here again, Webb is uncovering a surprisingly rich and diverse chemical cocktail. A survey of several disks using the MIRI instrument found a whole menu of carbon-bearing molecules. It found familiar ones like carbon dioxide and more complex ones like acetylene. And for the very first time ever in a protoplanetary disk, Webb detected benzene, a ring-shaped molecule that is a fundamental building block for more complex aromatic hydrocarbons. These findings show that not all planet-forming disks are the same. Some are very rich in water and carbon dioxide. Others are dominated by hydrocarbons. For example, the disk around a small star named J160532 was found to be packed with hot acetylene molecules, suggesting a very carbon-rich environment. A planet forming there would likely have a very different, carbon-heavy atmosphere compared to Earth. These discoveries are part of a major initiative called the Ice Age program, which is using Webb to trace the journey of these vital molecules, from their origins as ices in cold molecular clouds, all the way into the protoplanetary disks, where they get incorporated into new worlds. It's like being a cosmic detective, following the chemical clues that lead to life. For a long time, astronomers believed that certain environments were just too hostile for planets to form, especially Earth-like ones. The thinking was that massive, hot stars would blast their surroundings with intense ultraviolet radiation, effectively boiling away any nearby protoplanetary disks before they had a chance to form planets. But Webb is challenging these assumptions. In a groundbreaking study, Webb stared into the heart of one of the most extreme star-forming regions in our galaxy. It focused on a disk named XUE1, which is being bathed in ferocious UV radiation from massive stars nearby. Everyone expected the disk to be barren, but to their astonishment, Webb found clear signatures of both water and simple organic molecules in the inner part of the disk. How is this possible? Further modeling revealed that the disk itself acts as a shield. While the intense radiation was eroding the outer edges of the disk, the dense inner region, the rocky planet zone, was protected. It's a safe haven, a cosmic bunker, where the building blocks of planets can survive even in the most extreme neighborhoods. This discovery is a game changer. It dramatically expands the range of environments where we might find habitable, Earth-like planets. They might not just form around quiet, sun-like stars, but also in the chaotic, bustling stellar nurseries packed with giant stars. As powerful as Webb is, it doesn't work alone. Science is a collaborative effort, and Webb's power is amplified when combined with other observatories. Its most important partner is the Atacama Large Millimeter/Submillimeter Array, or ALMA, a massive network of radio telescopes in Chile. ALMA is an expert at studying the cold, outer regions of protoplanetary disks. It can map the large-scale structures of dust and gas in incredible detail. Webb and ALMA are the perfect scientific pairing. ALMA provides the wide-angle context, showing the overall structure and the reservoir of cold material in the outer disk. Then Webb zooms in with its infrared vision to study the warm, dynamic, planet-forming chaos of the inner disk. By combining data from both telescopes, astronomers can piece together the complete story of how a planetary system evolves, seeing how forces like radiation from nearby stars can either help or hinder planet formation. This brings us to the future. Everything we're learning about how terrestrial planets are born is a step toward answering the ultimate question. The study of protoplanetary disks is the first chapter in the search for life beyond Earth. By understanding the conditions and ingredients of their birth, we can better predict which planets might be habitable. As Webb continues its mission, it will begin to look at the atmospheres of fully formed exoplanets, including rocky ones. Its instruments can search for biosignature gases, molecules like oxygen, methane, and carbon dioxide in specific combinations that could point to the presence of biological activity. Now, this will be an immense challenge. We won't find a single silver bullet molecule that screams life. Instead, scientists will have to build a case, gathering evidence from many planets and using sophisticated models to rule out non-biological explanations. The James Webb Space Telescope is really just getting started. It has already fundamentally rewritten our understanding of how worlds like ours come to be. Its ability to see into dusty stellar nurseries, to taste their chemical makeup, and to see the shadows of forming planets is giving us a front-row seat to the process of creation. The journey has just begun, and as Webb continues to stare deeper into the cosmos, it will bring us closer than ever to knowing if we are, in fact, alone.